Here's our last example problem for Unit 3.2, and think of this problem as being something like a practice test. So here's the setup. We have two capacitors and a resistor that are connected together in a loop along with a switch. Now the switch is initially open, and for the sake of this example problem, let's say that capacitor number 2 is initially uncharged. And capacitor number 1 initially is charged up so that its initial amount of stored energy is equal to 12 joules. Here's the question. After a long time has passed, how much energy is dissipated in the resistor? After a long time, how much energy will have been dissipated in this resistor? Boy, that is tricky. That's quite the test, right? In other words, this represents a type of problem you haven't seen, but only relies on the principles that we've learned so far. So let's see if we can tackle this. There's actually I'd say, an easy way and a difficult way, and they should both lead to the same answer. So obviously we'll start first with what I think is the easier way. So now that you've got the question, let me erase. How about first thing we do is figure out what's the amount of charge that's initially on capacitor number 1. We know the charge initially on capacitor number 2 is 0 because we were told it initially stored 0 energy or was initially uncharged. So potential energy for a capacitor is equal to 1/2 charge times voltage. It's 1/2 capacitance times voltage squared, or it's charge squared divided by twice the capacitance. Let's go with that expression as a way to solve for the value Q, which represents the initial amount of charge before this switch is dropped. So if we cross multiply and take the square root of both sides of the equation, that amount of charge initially on capacitor number 1 must be equal to the square root of 2 times the initial amount of energy it stores multiplied by the capacitance. So let's plug in the numerical values and see what we get. 2 times 12 joules times 0.06 farads. That's another way of saying 60 millifarads, right? Grab a calculator, see what you get. Yeah, hopefully you get the same thing as me. Numerically, this is 1.2. Now, can you convince yourself that this is really 1.2 coulombs? If you'd like, hit pause now on the video and go through the exercise to verify that dimensionally the square root of the product of joules and farads actually is coulombs. Okay, now that you've verified that the units work out, let's carry on and say at some point in time later, so at time t equals 0, Q is the charge on capacitor number 1, and there's 0 charge on capacitor number 2. But let's choose a different time, just at some later time we'll call t, then an amount of charge has been conducted off of the first capacitor and onto the other. Right? Let's say that this upper plate is positively charged because it lacks electrons, and the lower plate was negatively charged. With the switch drop, some of these positive charges wind up on capacitor number 2, and some of the electrons, which make the negative charge, wind up also on the lower plate of capacitor number 2. And so let's say it develops a charge that we'll define as lowercase q. So that means the charge on capacitor number 1 is capital Q minus lowercase q. Well, something has to be the same for these two capacitors, right? The amount of charge on capacitor number 2 is not guaranteed to be the same as the amount of charge on capacitor number 1. Right? There's no guarantee that lowercase q is the same thing as capital Q minus lowercase q. Nope. What about the amount of energy? Now that some of the charge has conducted off of capacitor number 1, its energy is less than 12 joules, is the energy on capacitor number 1 equal to the energy on capacitor number 2 at this point in time t? No guarantee of that. The one thing that's guaranteed to be the same, let's just call this point A, and we'll call this point B. Now, here's the thing. If this later point in time is in the steady state, if we let this time approach infinite, then this charge lowercase q represents the final amount of charge that's going to be stored on capacitor number 2. And capital Q minus lowercase q is the ultimate amount of charge. So in the steady state, charge is done conducting, which means there's not a current flowing this way through the resistor, nor is there a current flowing this way. Any of the current that was involved in allowing for this transfer of charge is now gone in the steady state as time approaches an infinite value. And when there's no current through a resistor, there's no potential difference across a resistor. We know that when the switch is closed, this point I've labeled as A is the same electric potential as this point here that I might as well then label as A. If there's a current through the resistor, then there's no guarantee that the electric potential at point B is the same as what I'll call the electric potential at point C. However, we're going to consider steady state. There is no current through the resistor, and so I'm allowed to say that this point is also at electric potential B. So that's the thing that's going to be the same for the two capacitors once they reach the steady state a long time after the switch is closed. They both have to have the same potential difference across them. How do we find the potential difference across a capacitor? Easy. We just think of the most basic equation we know. QVC, right? The voltage across a capacitor is the ratio of charge to capacitance. So at some point, the initial amount of charge on capacitor number 1 has been reduced by the amount of charge that was transferred onto capacitor number 2. So if I divide that total amount of charge that still remains on capacitor number 1, that represents the voltage across capacitor number 1. That's the electric potential from point A to B across this capacitor. Another way to say the electric potential across points A and B is to express the voltage across this capacitor, which would be Q divided by C2. So let's do some cross multiplying. Capital Q minus lowercase q is equal to C1 over C2 times lowercase q, which means in step 3 we can say capital Q is equal to lowercase q times the quantity 1 plus C1 over C2, which means the amount of charge that ends up on capacitor number 2 is equal to the amount of charge that was initially on capacitor number 1 divided by 1 plus the ratio of C1 over C2. So let's solve for that and see what it is. We already found that the amount of charge initially on capacitor number 1 was 1.2 coulombs. If we divide that by 1 plus, what are the values? 60 millifarads compared to 40 millifarads. So 1 plus 60 over 40 is the same as 1 plus 1.5, or in other words, 2.5. And 1.2 divided by 2.5 gives us 0.48. Okay, now how does this help us determine what amount of energy was dissipated through this resistor? Well, remember, initially, this whole circuit stored an energy of 12 joules. Let's consider how much energy it stores after the charge has been transferred. So the energy on capacitor number 1 is equal to the amount of charge. Oh, by the way, if capacitor number 1 started out with a charge of 1.2 coulombs and 0.48 coulombs have been conducted off of it and onto capacitor number 2, then that amount of charge that remains on capacitor number 1 would be what? 0.72 coulombs. So if we take that 0.72 coulombs squared and divide it by 2 times 2 times 0.06 farads. I'm just using the equation. Energy stored in a capacitor is Q squared over 2C. So when I apply that to capacitor number 1, what I really mean is the difference between the initial charge and the charge that was conducted off of it. So what does this calculate out to? This comes out to 4.32 joules. Let's find the amount of energy in the steady state on the other capacitor. So that's going to be lowercase q squared over 2c number 2, or in other words, 0.48 squared divided by 2 times 0.04. Let's see what that comes out to. That comes out to 2.88 joules. So in total, in the steady state, we just need to add 4.32 plus 2.88, and we get 7.2 joules. So what happened? There was 12 joules stored in this capacitor before the switch was closed. The switch is closed, charge conducts. This no longer has a charge of capital Q. It's now the difference between its initial charge and the charge that develops on the other. And in the end, there's less energy, right? There was 12 joules, and now there's only 7.2. So where did that energy go? Well, in order for this charge to be conducted off of capacitor number 1 and onto capacitor number 2, a current had to flow through this resistor. And when current flows through a resistor, electrical energy is wasted as heat, is wasted as thermal energy. And so how much was wasted? Well, just the difference between the two. The change in energy is 12 joules minus 7.2 joules, or in other words, 4.8 joules. So that, I would say, is the easy way to get this answer. What's the difficult way to get it? I suppose it's not that difficult, but maybe it's not as intuitive. So we can say, if that's really what caused this 4.8 joules was the dissipation of energy through the resistor, then we need to say that dissipation comes at a certain rate. For a resistor, remember, power is either current squared times resistance, it's voltage squared divided by resistance, or it's current times voltage. Let's go with this expression here. However, this current is not a steady value because this is an RC circuit. What we really need to say is this current is equal to some initial current times e to the negative t over tau, right? So if I really want to get the amount of energy then that I can do, I can't just multiply a steady rate of power times some overall amount of time. In fact, the time would be infinite, and the power is changing due to the fact that the current is changing in time. It's better we say not that energy equals power times time, but rather energy is equal to the integral of P dt. When the switch is closed, that represents time t equals 0, and by the time all the energy has been lost and the capacitors reach their final steady state charges, an infinite amount of time has elapsed. So there are limits of integration. So we get that the energy, which is really the change in potential energy from the initial condition to the steady state, is equal to the integral from 0 to infinity of P dt, where what do we replace for P? I squared times R, and what do we substitute for I? I naught times e to the negative t over tau. So the loss of potential energy in this system is the integral from 0 to infinity of I naught e to the negative t over tau, quantity squared, times R dt. Okay, we can take some quantities out of the integral sign. The loss of energy should be I naught squared times R times the integral from 0 to infinity of e to the, now look, squared, right? That's why this I naught is squared. And I can't forget to square this, so this becomes e to the negative 2t over tau. Loss of energy is then I naught squared R, and then we evaluate the integral. We can take the antiderivative, I suppose. So this becomes what? Negative tau over 2 e to the negative 2t over tau, evaluated from 0 to infinity. I'd actually like to change this negative to a positive. Let me do that, and then I'll change my limits of integration from infinity to 0. So this is a constant. I can treat it as such, and I really just need to evaluate e to the negative 2t over tau from 0 to infinity. Now e to the 0 is equal to 1, and e to the negative infinity is equal to 0. So actually, when we apply the limits of integration, this term just goes away. So we should find that the loss of potential energy between the initial condition and steady state is tau over 2 times I naught squared times R. Now, what would this value of initial current be equal to? Well, that should be some initial voltage divided by the resistance in the circuit. And what's tau equal to? Well, tau is equal to the product of R and I'll say C equivalent for the circuit. Okay, so this R gets squared, but then that's going to cancel these values of R. So it turns out it doesn't matter whether this is a 500 ohm resistor, an 8 ohm resistor, 100,000 ohm resistor. That's going to affect how quickly it reaches the steady state, but it's not going to change the amount of energy lost, nor should it, because notice in our first attempt to find the answer for the amount of energy lost, we never had to consider the value of this resistor. So the loss of energy should be equal to 1/2 the equivalent capacitance of the circuit times the initial voltage squared. Now the initial voltage, let's see, we were told before the switch was dropped that this stored an energy of 12 joules, had a charge of 1.2 coulombs, and we know it has a capacitance of 0.06 farads. So I guess the initial voltage is all across this capacitor before the switch is dropped, and that's what's driving the current through this resistor. That initial voltage should be equal to 1.2 coulombs divided by 0.06 farads, which gives us 20 volts. Okay, what's the equivalent capacitance? Well, as that current flows through, this constitutes a loop, and so these capacitors should be treated as being connected in series. And remember, the rules for capacitors are opposite the rules for resistors when it comes to finding equivalent values. So two capacitors in series should have an equivalent value that we can calculate by taking the product over the sum, right? If we take 60 millifarads times 40 millifarads and divide it by 60 plus 40, what does that come out to? Hey, grab your calculator and double check. Yeah, I think you'd agree that comes out to 24 millifarads, or 0.024 farads. So, drum roll, let's see what we get. The change in energy should be equal to 1/2 times 0.024 times 20 squared. Grab a calculator, see what we get. And how about that? Comes out to 4.8 joules. My goodness, physics makes me happy. Thanks for watching.